Hello all, welcome to this course on time series modeling and forecasting using R. So throughout this week, just to give you again a very quick refresher, so we've been talking or rather focusing more on non-linear time series processes, and today's session would be the last session from a theoretical point of view. So of course we have one more session which would be a practical session in R, but so far I'll just sweep you all of you through what we have covered so far this week. So we started building upon the motivation behind why should one switch from a linear time series structure to some sort of a non-linear time series structure. And then we gave an idea or rather an introduction about regimes. So in this entire literature, there is a very profound kind of suitability of this term regime. And again if you're not confident about any of the terminologies or definitions, again you can always go back to some of the previous lectures or previous videos in this week. So again, what do you mean by regime? So regime is nothing but different states within a time series process, and one strong assumption is that each of these different states or each of these different regimes should have some dynamically different characteristics. Okay, and throughout this entire week, so over the last 3 sessions I've been giving some visual explanations as well, right. So let's say if you have an overall non-linear kind of a structure, but and then let's say you have some threshold values, let's say 2 threshold values or 3 threshold values. So depending upon the number of threshold values you have, we are kind of dividing the overall time series into those many regimes. And one again a strong assumption is that even if the overall time series becomes non-linear, but within each regime or within each phase or within each state, I can apply some sort of a linear time series process, let's say AR or ARMA or ARIMA, something like that. Okay. And in this period we talked about the very first kind of a non-linear time series model, which is TAR model or threshold autoregressive time series process. Okay. And then towards the end of let's say last session or last to last session, we talked about multiple other extensions of TAR model, let's say SE TAR model, which is called as self-exciting TAR or MTAR or star model, right. So all these are kind of, they sort of point towards different characteristics within the non-linear time series framework, and then sort of pointing to different ideas about, let's say if you have let's say a different transition function, then what would happen. So again if you remember, we discussed number of different kinds of regimes, right. And again if you remember vaguely, so we talked about 3 different kinds of regimes. So the first one was based on a threshold value, the second one was based on a smooth transition function. So if while a time series switches between or rather over a threshold value, if its switch is sort of a smooth in a gradual manner, then we end up being in the second case. And the third is the focus of today's session right here. So if you see the title here, we'll talk briefly about something which is called as Markov switching models. And again this was seen earlier as well as a third category of kind of a regime where you have a probabilistic kind of a view. Okay. So rather than the transition function being smooth or you have some sort of a threshold value, but what would happen if you bring in some idea of probability. So let's say you have a probability transition matrix sort of, right. Then that category of models or that category of regime techniques are called as Markov switching models. Okay. So hopefully up to now there should not be any confusion. So again I'm pretty sure that almost all the topics here might be new to many of you. And again as mentioned or rather given as a small disclaimer towards the beginning of this week's lectures, that this entire area about non-linear time series processes is not discussed often in a routine time series sort of a course. Okay. So hence you would want to put a bit more attention to each and every let's say model structure of TAR or model structure of star. How is star different from TAR, right? What is the advantage of let's say star over TAR? So all these small things if you keep in mind, then hopefully when you get into the practical session, the next session, it should not be any problem. Alright, so we will start with the title today, which is Markov switching models. Again as always a short introduction about let's say Markov switching models. So again in short they are called as MSMs or Markov switching models, and these are a class of non-linear time series models. So again idea is that we are trying to capture non-linearity within the time series that capture regime switching behavior by assuming that the transition between regimes is governed by some sort of a hidden Markov process. So, okay, so I will say that this is the most important differentiating point when it comes to let's say Markov switching models or star models or rather TAR models, etc. Okay. So again just to repeat that the differentiating point between MSMs is that the transitioning between the regimes by any practical time series is governed by something called as a hidden Markov process. And second point is, unlike the TAR models or threshold autoregressive, or rather the SE TAR model or the self exciting TAR models, where regime changes depend on observable variables, right. So, we have seen this in the past as well, that if you take up, let us say, a TAR model or a SE TAR model, then all the regime switches or all the regime transitions depend on some observable variables, and these observable variables are nothing but the threshold values. Okay. And again, we kind of assume that usually we can take the threshold values to be some sort of a lagged values of the time series themselves. So, let us say if you are taking yt as a time series, then I can have something like yt minus 1 to be the threshold value, and so on and so forth. So, I will write down etc. here. So, again it need not be yt minus 1 every time, it can be some lagged value of the actual time series yt itself. Okay. But the underlying fact between these two models, so TAR and SE TAR, is that the regime changes depend on observable variables, and on the other hand, MSMs allow the regime to switch probabilistically based on some unobservable state variable. So, I think just to one last time press on the differentiating aspect is that if you take up TAR model or any of its extensions, let us say STAR or SE TAR, etc., then all the regime switches depend on observable variables. So, I will highlight this. Whereas, if you come to Markov switching models, then all the regime switches occur probabilistically based on some unobservable state variable. Okay. So, MSMs, the regime switches happen using an unobservable state variable, whereas the usual TAR models or SE TAR models, the regime changes or the regime transitions depend on observable variables. Make sense so far? Okay. So, now the next thing is, what are the key features of the Markov switching models, right. So, key features of the MS model. Again, as always, so probably all these pointers you must have seen even in the last session when we talked about, let us say, key features about the other models. So, TAR model or STAR model, SE TAR model, etc. So, the first one is regime switching. So, the time series can exist in multiple regimes. For example, let us say high volatility, low volatility, right, etc., each with its own set of parameters. So, there has to be some regime switching which has to be performed underneath the practical time series. Okay. Now, here one extra feature, and again the most important one, is the Markov process. So, what do you mean by that? So, all the regime transitions are governed by a first order Markov process, meaning the current regime depends only on the previous regime. Okay. Now, this is one very useful characteristic of any Markov process. So, again I am not sure that how many of you are familiar with, let us say, Markov process or in general the Markov property. So, the Markov property means that, let us say, if you are sitting today, let us say yt. So, information of yt only depends on one past value, let us say yt minus 1, and that is all. So, this is called as a Markov property, and if you create an entire time series structure or rather a stochastic structure using this property, that process would be called as a Markov process. Similarly, here we have an underlying idea about a Markov process inbuilt in the MS models, and again how exactly? So, all the regime transitions are governed by a first order Markov process. What do you mean by that? So, meaning the current regime depends only on the past regime or one previous regime. Now, third important aspect here is the hidden states. So, you have to assume that some states are hidden, that the regime is a latent or rather unobservable variable inferred from the data. Okay. So, here I think the most important or rather the key differentiating point is that all these regimes are sort of brought from some unobservable variables which are called as latent variables, and hence all these regimes or all these states are called as hidden states. Okay. And lastly, flexibility as always. So, suitable for capturing abrupt or smooth transitions dependent on the state transition probabilities. So, depending on what are the state transition probabilities, we can actually govern if the transitions would be smooth or they would be abrupt and so on and so forth. Okay. So, hopefully if you understand the key features of the MS models, I think pointers 2 and 3 are sort of differentiating from, let us say, either TAR models or STAR models, etc. And again, just to repeat one last time, is that all the regime transitions are governed by some unobservable variables or rather latent variables or some probabilistic kind of a manner. Okay. Alright, so now we will pay attention to the actual model formulation. So, a simple Markov switching autoregressive model, so in short MSAR. So, again the key here is that such a model also consists or rather based on an autoregressive kind of a structure as before, right. All the models we discussed so far sort of depend on some autoregressive structure which is inbuilt in that, right. Similarly, here a simple Markov switching autoregressive, in short MSAR model with k regime. So, let us say the number of regimes is k, is defined as follows. So, yt equals mu st plus phi st comma 1 yt minus 1 plus phi st comma 2 yt minus 2, so on and so forth, up to phi st comma p yt minus p plus some random error. Now again, paying attention to all the notations. So firstly, what do you mean by st? So st is the key notation here, which is nothing but the latent state or latent regime at time t. Okay. So again, st is the differentiating notation if you compare this model structure with, let's say, tar model structure or star model structure, etc. Okay. So the extra thing here is st, which is nothing but the latent state or latent regime at time t. And by the way, again, just to remind all of you that this st is being a latent state is unobservable. Okay. So all these st's are unobservable here. Okay. And this st can take values between 1, 2, 3, 4 up to k, because how many regimes you have? So you have k regimes, right? And similarly, mu subscript st is a regime specific mean. So corresponding to that regime, how much is the mean is characterized by or given by mu st. Make sense? And lastly, phi st comma I are as usual the AR coefficients within the regime st. Okay, and et is the error term with variance sigma square st. So let's say we are assuming that this et is a random error term having this as the variance. Okay. So hopefully model structure should be understood. Otherwise, if you don't understand some of the notations as to what is going on in this MSAR kind of a model, then probably it might not be very helpful in the later stage. Okay. So again, if you want, I can repeat one last time, is that st is the latent state or latent regime at time t, taking values between 1, 2, 3, 4 up to k. Mu st is the regime specific mean. Phi st comma I are all the AR coefficients in regime st, and et is the error term with assuming that the variance is sigma square st. Okay. So this is broadly the model structure of the MSAR model with k regimes. Okay. Now the second important ingredient is we have to define some sort of a transition probabilities, right. So this entire idea about regime switching underlying this MSAR model, or in general any Markov switching model, is controlled by a state transition probability matrix, which is given by capital P here, right. So this matrix that you see, which is capital P, is called as a state transition probability matrix. And again, I am very sure that we have discussed this in some of the past lectures this week, right. So again, if you vaguely remember that we had put down a similar matrix, and then so if you remember while discussing the three kinds of regimes, right, and then the third kind was exactly this one, which is Markov switching regime, we had kind of introduced the notation about a state transition probability matrix. So similarly here, the only idea is that we are kind of extending this to more than 2 up to k, because we are assuming the number of regimes are k, right. So again, just to press on that fact that number of regimes equals k. So this matrix would be a k cross k matrix. Okay. So if you want the order of the matrix, it would be k cross k. Now what exactly are all the individual items in this matrix? For example, P11 or in general Pij. So what do you mean by Pij? Where Pij is nothing but probability that St is j while St minus 1 was I. Okay. So the current regime value is j, but the last regime value or one past regime value was I. So in short, it means that probability of transitioning from regime I to j, because last regime was I, current regime is j, and how much is the probability that the time series would transition from, let's say, regime I to regime j, basically. Okay. So I am pretty sure that understanding this state transition probability matrix should not be difficult at all, right, because all these are sort of probabilities which, and each probability has two subscripts, right, something like Ij. So think that I is the last regime state, j is the current regime state, and how much is the probability that it will make the transition from regime I to regime j. That is all. Okay. And by the way, one very important property is that each row of P sums to 1. So if you take a sum of any of the rows, let us say something like this, summation P and then I j, or rather 1 j, let me write down 1 j, and then j going from 1 to k, this has to be 1 for all j, for all j. Okay. Make sense? And then if you take a sum over any of the rows, it has to be exactly equal to 1. Alright, so now we will pay attention to estimation part, right. So how does one estimate? So again, we can make use of some of the standard techniques, let us say create the likelihood function. So the joint likelihood of observed data and hidden states is maximized. So once you create that likelihood function, then how do you maximize that? How do you get hold of the MLE, etc. But here it might require marginalizing over the latent state. So you would want to find out the marginal distribution over the latent states. This is an added step here, which has to be performed. Okay. The second kind of an estimation kind of a technology, or rather not technology but method, is expectation maximization algorithm, or in short EM algorithm. And again, this EM algorithm is widely applicable not just in time series but across any of the other statistical literature as well, right. So, EM algorithm contains two steps. So, the first is called as the E step, which calculates the expected values of the hidden states given some set of parameters, right. So, this is the expectation part, or the E step, and the second step is M step, or the maximization step. So, the M step updates the parameters to maximize the expected likelihood. Okay. So, rather than writing down a joint or some sort of an overall likelihood function, what we do is we run this algorithm in two levels. So, the first level is E step, which finds out the expected values of all the hidden states given some observable set of parameters, and once the E step is done, then the next step is M step, which updates the parameters to maximize the expected likelihood. And then the third kind of a estimation technique is filter and smoother. So, this is slightly technical, again we will not go into details as to what exactly do you mean by filter, what do you mean by smoother, but just a couple of pointers here, that in literature these two filters exist. So, Hamilton filter estimates the probability of being in a particular state at time t, while the Kim filter smooths the probabilities to improve the state estimation. Okay. So, hopefully the idea about estimation should be clear as to what are the different techniques that one can estimate the underlying parameters of a Markov switching kind of a model. So, it could be either using a likelihood function or the EM algorithm, or using a filter and a smoother kind of a technique, etc. Now, what exactly are the advantages of MS models, right? Again, as always, flexibility, so can handle both abrupt and gradual transitions between regimes. Second is state dependence. So, what do you mean by that? So, incorporates dynamics specific to each regime, improving its model accuracy. Okay. So, incorporates dynamics specific to each regime, because again as discussed number of times in this entire week is that each regime is entirely different, or rather could be entirely different, having different sets of dynamics. Okay. So, state dependence means that incorporates dynamics specific to each state or specific to each regime, improving the overall model accuracy. And thirdly, latent regime modeling, which infers unobservable states that drive the system. Okay. And similarly, on the other hand, what could be the challenges in MS model? So, again computationally complex, right. So, this MS idea is not very straightforward, because you have to get an idea about the transition matrix, and it involves some sort of a probabilistic kind of a view, right. So, computational complexity exists, which means that estimation involves maximizing a high dimensional likelihood function. So, it may turn out that the overall likelihood function which has to be maximized is a high dimensional likelihood function. So, containing lots of parameters, or lots of levels, etc. Secondly, the other challenge could be model selection. So, choosing the number of regimes firstly, and lack structure requires care. So, how many regimes should you have, and up to what lag in the past should you go? So, the lag structure and the number of regimes require some care. Thirdly, interpretability. So, regime probabilities must be carefully interpreted. So, when you create that capital P matrix containing all the transition probabilities, then each and every switching probability, or rather regime probabilities, must be carefully handled or carefully interpreted. And lastly, overfitting. So, adding too many regimes can lead to overfitting, as seen in the earlier models as well. Okay. So, these are some challenges when it comes to MS models. So, I will say that model selection, computational complexity and interpretability are slightly on the newer side, while of course overfitting is always there, right. So, if you add in too many regimes, not just in the MS kind of a model, but even in TAR models or STAR models, then that can lead to some overfitting. Now, what we will do is I will show you one particular numerical example. So, since we are almost through with covering all the theory, so I will talk about one numerical example, and then this would be helpful in understanding as to how do you create that transition matrix and how do you fix some of the values, etc. Okay. So, a small numerical example demonstrating a Markov switching autoregressive or other MSAR model containing two regimes. Okay. So, let us say number of observations is fixed to 300, the mean vector is fixed to 1 comma minus 1. So, since you have two regimes, then each vector should contain two values. Okay. Then the phi vector is 0.8, 0.5, this contains the AR coefficients, and the standard deviations of the error terms is 0.5 comma 1, and this is the probability transition matrix. Okay. And again, one characteristic is that if you sum over any of the rows, it should be 1. So, 0.9 plus 0.1 is 1, while 0.2 plus 0.8 is also 1. Okay. Now, by the way, all these values are kind of hypothetical values. So, there is no backing to it. So, this is just some random values. Okay. But then what? So, let us say once you fix all these ideas, then the next step is estimation, right. So, estimation interpretation or rather estimated parameters. So, the mean value which is mu, the AR coefficients given by phi and variance given by sigma square for each regime has to be estimated. Also, the transition probabilities, let us say Pij, that show the likelihood of switching between regimes. So, all these are considered to be parameters which have to be estimated. So, let us say mu, phi, sigma square and also Pij for each state. Okay. And then secondly, hidden state. So, smoothed probabilities indicate the likelihood of the time series being in each regime at a given time. So, you have to carefully address the idea of hidden states or estimation in general. Okay. Alright, so let us say if you run this entire code in some software, let us say R or Python, wherever, and then you try to estimate all the parameters given the sets of input values which we saw in the previous slides, then this is exactly one set of estimation that the software throws at you. So, inside regime 1, what happens is the mu 1 is estimated to be 0.98, phi 1 is estimated to be 0.81, while sigma 1 is estimated to be 0.52, and similarly in the regime 2, the mean value is minus 1.02, phi 1 is 0.48 and sigma 1 is 1.05. Now, again just to compare these estimated values with the actual values, again if you remember vaguely that what values we fixed earlier. So, our mu 1 was something like 1 if I am not wrong, my mu 2 was something like minus 1. By the way, here we have a small typo. So, this should be mu 2, this should be phi 2 and this should be sigma 2 basically. Okay. So, my mu 2 was minus 1, my phi 1 was, again let me go back couple of slides. So, my phi 1 was 0.8, phi 2 was 0.5, and again you can clearly see that the estimations are kind of really close to the fixed values. So, phi 2 was 0.5, while lastly my sigma 1 if I am not wrong is 0.5 and my sigma 2 was basically 1. And similarly transition probability. So, these are the estimated transition probabilities. So, P11 is 0.89, P12 is 0.11, P21 is 0.19 while P22 is 0.81, and each one of these is sort of close to the fixed values in that probability matrix which is capital P. Okay. So, the summary of output is giving us a very good indication as the estimation has been performed quite well here. Now, the output interpretation. So, the parameter estimates let us say mean, the AR coefficients and variance sigma square for each regime and transition probabilities between the regimes. So, the outputs give you these things, right. So, parameter estimates of all these ideas. Secondly, plot of smooth probabilities. So, if somebody is interested in let us say plotting the smooth probabilities would show the likelihood of being in each regime over time. Okay. So, one can actually plot the different transition probabilities, it would show the likelihood of being in each regime over time. So, what is the probability of let us say switching from one regime to another or second regime to third, etc. And thirdly, diagnostics. So, validate the model by checking the residual. So, once you do the estimation part and once you fix some model on the parameters, on the data and so on and so forth, then the last step has to be always diagnostic checking. So, validate the model by checking the residual performance. Okay, so now we will very quickly pay attention to some other possible interesting extensions, right. So, the first kind of extension is called as bilinear models, and then how are they different. So, let us say incorporate products of past observations and some noise to handle non-linearities, and such bilinear models have a capability of including some interactions. So, here if you see we are sort of multiplying these two coefficients, right. So, beta jk multiplied by yt minus k. So, you are sort of bringing some interactions in the time series structure. And what are the applications? Let us say used for time series with interaction effects such as finance or environmental data, etc. Okay. So, one extension is bilinear model. The another extension could be non-linear ARX model. So, what do you mean by that? So, models output as a non-linear function of past inputs and outputs. So, this could be treated as you have a time series which runs like that in terms of yt, and on top of that if you have some other exogenous inputs as well or some other independent variables which are given by xt's, and then you have a function combining xt's and yt's, then such a model is called as a non-linear ARX model. So, by the way, ARX stands for autoregressive exogenous, right. So, X stands for exogenous inputs. So, on top of the autoregressive structure, if you have some exogenous inputs as well, then we can have a model which is called as non-linear ARX model. Okay. So, So in this case, f can be a polynomial, neural network, or some other nonlinear function. And application wise, it's seen in control systems, dynamic system modeling, etc. Okay. Third one could be neural network based model. So let's say a nonlinear autoregressive neural network, or in short NAR/NN, uses a neural network to model the autoregressive relationships. By the way, the entire next week would be spent on, let's say, machine learning and time series integration. So there again we'll talk about, let's say, characteristics of, let's say, NAR model or NAR/NN model, etc. Okay. Flexible and powerful, especially for complex nonlinear dependency. So one can go the neural network route if you want to sort of perform some complex or rather capture some complex nonlinear dependencies. Okay. On the other hand, LSTM. So again, I am pretty sure that most of you might have heard about this term. So long short-term memory handles sequential dependencies and long-term memory in nonlinear time series. Other possible interesting extensions could be, let's say, smooth transition Garch or rather ST Garch. So extends Garch by allowing regime switching in the variance equation. So we've studied Garch extensively in the last week. So can we extend a Garch model with by bringing some smooth transition functions? So it's called as ST Garch model. Or on the other hand, let's say hidden Markov model, so HMM. So captures switching dynamics in time series using discrete latent states. Then functional time series, let's say useful for high dimensional or infinite dimensional time series data, models temporal changes in curves or functions. And lastly, wavelet transform models decompose the time series into different frequency components and useful for identifying and modeling non-linear periodic patterns. Okay. So again, the literature behind or rather inside this non-linear time series modeling forecasting is vast, right? So we have discussed a lot of extensions which is kind of interesting and applicable to many more complex kind of situations. So one should always choose the correct model depending on the intricacies in the underlying data set. Okay. Thank you.